7.1, integral as a net change. Example 1, a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. Okay, well, where t is the time in minutes and t is from 0 to 60. Find the amount of the chemical that flows into the tank during the first 20 minutes. So you got to break these down. First 20 minutes means from 0 minutes to 20 minutes. This here is the rate in this class. Okay, when you think of rate, you better automatically think derivative. So I have the derivative. Basically, I want to figure out how many, or not liters, right? Yeah, how many liters flowed out of this tank. So you're going to integrate from 0 to 20 minutes, and you're going to integrate the derivative in order to get the amount of liquid, liters, chemical, whatever it is. So integrate. Let's see. 180t plus 3 over 2t squared, and I'm evaluating that from 0 to 20. So plug in the 20, plug in the 0. 180 times 20 plus 3 over 2 times 20 squared. And then minus, or oops, minus, plug in the 0, so 0 plus 0, 120 times 80 is, what number is that? 3600 plus, and then so 20 squared, that's 400. 400 times 3, 1200 divided by 2. 3600 plus 600 equals 4200. And that's how much, that's how many liters. 4200 liters flowed out of the storage tank. Okay, example 2. I got a little boo-boo. I left out the square. That's supposed to be 10t squared. Oopsie. Okay, the velocity in feet per second of a particle moving along a line is v of t equals t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. Okay, so part A, what is the displacement of the particle on the time interval from 1 to 5? So the displacement is basically the difference from where it was to where it ended up. And we've actually already done this. Displacement using integrals is basically the net area between the curve and the x-axis. Remember, the net area, the negative area gets subtracted from the positive area. So displacement is just a regular integral. So t cubed minus 10t squared plus 29t dt from 1 to 5. I'm not going to solve this manually because we should be at the point that we can integrate this equation and plug in 5 and then plug in 1. And to speed things along, you can plug this into your calculator, and it's math number 9, and plug in the stuff, and you essentially get 32 divided by 3, and that's feet. Of course, you can get a decimal. So that is the displacement of the particle. From 1 to 5, it was displaced 32 divided by 3 feet, or 32 thirds. B, what is the total distance traveled by the particle? So total distance Whenever you see that, you need to think of total area. And remember, total area, I don't care that the area is below the x-axis right there, because that would be negative. I'm still counting it, so we make it positive. And net, or total area, is still an integral, but then that's when we use the absolute value. We have done this before. I've already done this in notes. It was called the section, I don't remember what section it was, but I titled the example net versus total area. So we would be integrating this. Oh, not a parentheses, it's the other absolute value. And then you can get some practice doing this on the calculator as well. It is math, number 9. But then you have to go back to math and move over to number, I believe. And then it's number 1, and it says ABS, which just stands for absolute value. And then you plug it in, and you should get this. And that's how much the particle actually traveled. Now, not the amount that it was displaced. Remember, let's say this is your house. And here's your job. And here's the park. If you start traveling from your house and go to the park, and then from the park go to your job, and let's say this is 10 miles and this is 15 miles. You have traveled a total distance of 25 miles. But your displacement, your displacement, let's say your house is 8 miles from your job. Since this is where you started and this is where you ended, your displacement is just this, the 8. Okay, total distance and displacement are two different things. Even though you traveled from here to here, your displacement doesn't count all of that. It just counts how much you actually moved. Okay, so that was part B. Alright, example 3. A car moving with initial velocity of 5 miles per hour accelerates at the rate of a of t equals 2.4 t miles per hour per second. Now notice, miles per hour per second. Really weird. It comes up a lot. For 8 seconds. A, how fast is the car going when the 8 seconds are up? Okay, well first of all, they told you something other than the equation. They told you that the initial velocity was 5 miles per hour. Okay, so that means when v was, or the t, sorry, when t was 0, the velocity was 5. So to start off, this car, right from the get-go, was going 5 miles per hour. So you're going to have to do something with that information. Acceleration is 2.4 t. Now, how fast is the car going? Let me break that down. How fast means what is the velocity? How fast is the car going when the 8 seconds are up? The 8 seconds are up means at t equals 8. So basically, what is the velocity at t equals 8 for this car? So if we have acceleration, in order to find velocity, well, the velocity is the function I would derive to get acceleration, right? So acceleration is the derivative of velocity. So if I want velocity, I would integrate acceleration. But I also have to take into consideration that this car already had an initial velocity. So that's going to go here. This is the initial velocity of 5 miles per hour, so it's already traveling at that. And then when time started changing, right, at from 0 up, 1, 2, 3, 4, 5, 7, 8, the acceleration increased, or the velocity. Okay, so here's my equation basically. This is what I'm integrating. So I get 5 plus, and I'm integrating this from 0 to 8. Right, because I want to know what is the velocity at t equals 8. So from 0 to 8, and then 2.4 t dt. So you would integrate this. So 5 plus, and then 2.4 t, but now it's squared, divided by 2. And this is getting evaluated from 0 to 8. So let's see. 5 plus 1.2 t squared. And then essentially, because I have limits, I don't have to worry about c. But this will work as my velocity function when I'm not having to worry about c. And I am going to go ahead and plug in the 0 and the 8, right? So 5 plus, all right, let's plug in 1.2 times 8 squared minus 1.2 times 0 squared. So 5 plus 64 times 1.2, which is 76.8. There you go, I believe. And then add those babies together, and it should be 81.8 miles per hour. Now remember, 5 is the initial. The car was already moving at 5 miles per hour. And then they want to know how fast it was going when it was 8 seconds. So you have to add those 5 miles that it was already traveling, 5 miles per hour. And then from 0 to 8, it calculates, the integral will calculate the velocity from 0 to 8. So then you add the initial velocity plus the velocity from 0 to 8, and then you get 81.8 miles per hour. Oh, part B. Oops. So part B, how far did the car travel during the 8 seconds? Okay, so how far, this means distance. And to find distance, that is the same as finding total area. And during the 8 seconds means we're going to work with 0 to 8 again. But this time, in order to find the distance, what I'm going to integrate is not acceleration, it's velocity. Right? Because position, if I derive that, I get velocity. And if I want to find distance, position is what I would use. The original ft or x of t, the position function. So to find distance, I'm going to integrate the velocity from 0 to 8. Now, velocity, because it's total distance, I'm going to have to put that in absolute values. And I don't exactly have the equation for velocity. What I have is somewhat the equation, right? This part right here. Oh, let me do another color. This part right here, but without the limits. Now I can use that and not have to worry about c, because since I have limits, right? C goes away anyway. So I'm integrating from 0 to 8, and absolute value, right? A 5 plus 1.2 t. And that is, or squared, sorry. And that's what I would be integrating. Now, remember that from before, this was miles per hour per second. So you have to remember that from the very first part of this. I think I need to go on a sidebar because this is where I kind of lose people with the units of measure. So in the beginning, there was man. No, in the beginning, of this problem, if you read, it said miles per hour per second. Now, we integrated the acceleration, right? And to find the velocity. Now, the change in velocity is equal to acceleration times time. Now, this was miles per hour per second. And if you look at the problem, we're dealing with seconds. And so when I integrated, these canceled out, and I was left with miles per hour. Well, now I'm looking for distance. And distance is rate times time. Well, our rate is velocity, and velocity is miles per hour, and the time is seconds. So now we're back to miles per hour per second, right? Um, I know it's a little weird. Oops, I mean times. Oops. Uh, my bad. So now this is our new units of measure. So when we are done finding the total distance, my unit of measure is not just going to be miles per hour, it's going to be miles per hour per second, or time second. It just looks really weird. And it's not usually something you hear about. Anyway, okay, so back over here. I just wanted to make sure I cleared that up because usually people don't. I have I have trouble getting the correct units out when kids do work. Okay, so you integrate that. Again, I'm going to let you do it on your calculator to save some time. So you plug that in the calculator with the absolute value, and you get this, or you should anyway. And then this is miles per hour times second, times second, seconds. I know, it's really weird. Now, distance should be in miles. It shouldn't be miles per hour times seconds. That's not a unit of measure that we normally work with, right? Like what is this? What is this? You know? So, what is it? Chemistry where you is it chemistry where you go back and forth between units? So 244.8 miles per hour times second, right? Seconds. If I want to convert that to just strictly hours, I mean miles, because that's something we know about, distance, miles, right? You would multiply by the number 1. And I would multiply by hours and seconds, because those are the units I want to get rid of. I want to keep miles. So, 1 hour, right, is how many seconds? So let's see, 60 minutes is an hour, 60 seconds in a minute. So 60 times 60, that's how many seconds I have. So now we say bye-bye to seconds, we say bye-bye to hour, and we're left with 244.8 miles divided by that, and we get 0.068 miles. That is the distance traveled. Okay. Uh-oh. All right. From 1970 to 1980, the rate of potato consumption in a particular country was C of T equals 2.2 plus 1.1 T millions of bushels per year. with T being years since the beginning of 1970. How many bushels were consumed from the beginning of 1972 to the end of 1973? So we're concerned with the amount of bushels of potatoes consumed since 1972 all the way through 1973, and then all of 1973, right? So it was 2 full years. So from 1972 all the way through the end of 1973, which is essentially the very beginning of 1974. So from 1970, so 1971, 1972, 1973, 1974. So this is 0, this is 1, 2, 3, 4. That's the fourth year. We're concerned with the amount of potatoes sold between the start of 2 and up to the beginning of 1974. So from 2 to 4. We're trying to find the total amount, and we're given a rate, right? So this is the derivative. To find the whole amount, we're going to derive the derivative. So, or not derive, sorry, integrate. And we're integrating it from the second year to the fourth year, because that'll get me the amount sold or consumed between from 2 to 3 and from 3 all the way up to the beginning of 4. So 2 to 4. And then this is a great calculator question. You plug this baby right in there. 2, 4, 2.2 plus 1.1 t dt. And see what you get. And what you should get is 7.066 millions of bushels, right? Because that's what the units of measure here were. Where is it? Where is it? Where is it? Millions of bushels. Okay, next. A pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour as shown in the table. How many gallons were pumped during that hour? So again, we're looking for this total, this idea of total of everything. But I don't have an equation here. So this is data. We're using a table. And I don't have an equation, but I have to be able to understand that if I integrate that rate, that'll give me the total, okay? The amount of gallons pumped during that hour. Now, the time or the units of measure is gallons and then minute. And here we're working with from 0 to 60 minutes because it's an hour. So from 0 to 60. And I don't have an equation to actually integrate, so what I'm going to actually do is the area. Now this is an opportunity for LRAM, RRAM, MRAM, but the most accurate approximation that you can ever use is trapezoid. So I want you to try, unless it says otherwise, to use trapezoidal approximation. Because if you recall from the notes, trapezoidal approximation is actually an average of LRAM and RRAM. You add them together, divide by 2, and it is trapezoidal. So we're going to do the trap. Now remember, the equation for area of a trapezoid is 1/2 times the height, and then base 1 plus base 2. Well, if you recall, you still are going to use the 1/2. And then the height is actually your widths of the intervals. So that's 5, that's 5. Oh, goody gosh, if you look, they're all 5. So yay, it's the same interval. And then we're doing base 1 plus base 2. So here are the bases. So I'd add those two together. And then I would add these two together. And then I would add these two together. And I would add these two together. And so on. So as you can see, this one's being doubled, that one's being doubled. Like I'm adding those twice, right? So the formula goes, and please recall, we have done this before. I'm sliding this down here. The formula goes, you're going to take the first number and you're going to add it to twice the second. And you're going to keep doubling every single number until the very end. So this one doesn't get doubled and this one doesn't get doubled. Plus 2 times 64 plus 2 times 58. And I'm just going to keep writing it, okay? Alright, I finished writing it. So I multiplied every single number by 2 except for the first and the last. And so now, simplify. So 5 halves. And in the parentheses, if you add all of those up, you get 1433. Multiply by 5, I get 7165 divided by 2, which is 3,582.5 gallons. And what was it that was drowning out of here? It doesn't say what, but that's the total amount of gallons. I just don't know what kind of gallons. Gallons of what? Alright. Last example. The graph of the velocity of a particle moving on the x-axis is given. The particle starts at x equals 2 when t equals 0. Okay, so find where the particle is at the end of the trip. Okay, so at the end of the trip, I want to know what is the position, right? The particle is at the end of the trip where? I want to know the position at the end of the trip. And the end of the trip, according to the graph, is 10, at 10 seconds. So what I want, and if you look up here, the particle starts at x equals 2 when time is 0. That means the function is called x. When I plug in a 0, the function is equal to 2. Okay, whenever there's an x and a t, they're calling the position function x. Okay, x of t. They can do that. Sometimes they call it s of t. I'm trying to think of anything else, but that's basically s of t or x of t. Okay? Alright. So, this is the last time, right? So what we're looking for is this. What is the position when t equals 10? Okay, so the only thing you can do with this is a graph. I mean, I can find the area here, here, and there, but that's integrating. And so this is the velocity function, right? This is velocity, so this is v of t. So if I want the position function, I would integrate v of t from 0 to 10. And I'll show you why. Okay, so you integrate velocity, right? I don't have an equation, so I actually need to figure out what the areas are. So in this little triangle, it's 1/2 times base times height. So the base is 2, the height is 3, so 3 times 2 is 6, times 1/2. So this has an area of 3. Over here I have 3 times 3, so that's 9, times 1/2 is 4.5. Down here I have a trapezoid, not a trapezoid. No, yeah, that's right, trapezoid. Oops. I have a trapezoid, so 1, 2, 3, 4, 5. 1, 2, 3, so that's 8. The height is 3. So 3 times 8 is 24. Cut that in half. This is negative 12, right? So the area here is 3 plus 4.5 minus 12. So that's it. 3 plus 4.5 is 7.5. 7.5 minus 12. I went brain dead just now. What is that? Okay, 4.5. So 3 minus 12 plus 4.5 equals, it's 4.5, right? Yeah, I'm not crazy. Okay, so 4.5. Okay, so I know, according to the net change theorem, if I integrate something, right, the thing I tried to cram into your brains, if I take the integral of little f, let's do little f, from a to b, that is big F of b minus big F of a, right? So I'm going to use that same logic here. The integral of v of t would give me x of t, right? From 0 to 10. So x of 10 minus x of 0 would be the integral, right? But I already know what it equals. It equals 4.5. Now remember, this is what I'm trying to look for, right here. This is what I want. That's what I need. I already know that this equals 4.5, but see, x of 0, what could that possibly be? Oh yes, they told us that. Right here, x of 0 is 2. So, algebra, right? Using algebra, x of 10 minus 2 equals 4.5. Add 2 to both sides. X of 10 equals, oh, sorry, negative 4.5. I forgot the negatives. That's definitely negative. Add the 2, and I get negative 2.5. And that is my position at the end of the trip. All right, B. Find the total distance traveled by the particle. I'm using the same graph. I just wrote it down here. Now the total distance, remember, total means that I want to know everything that was traveled, even if it was negative. We're just going to make it positive. This is total area. Okay, total area. Everything that's positive, I'm just going to make negative. So it's basically the same idea, just that the equation, or the integral this time, is going to look like this. Because of the absolute value, it's still from 0 to 10. And I'm still using area. This was 3, this was negative 12, and this was 4.5? Yeah. So this time, we're going to add everything together, and anything that is negative will just get eliminated by our absolute values, or you could just make it positive, however you want to look at it. No big deal. So now it's actually 3 plus 12 plus 4.5, which is 7.5, 19.5. Okay, that's the total distance. And this was, I guess, meters. Okay. Oh, I guess above was meters also. All right, homework. 1, 2, 3, 4, 5, 6 questions. You'll have the first 30 minutes of class to complete that and turn in. Then we're going to do the multiple choice. You're only getting 30 minutes, whatever you answer in those 30 minutes. And then directly after that, you're going to do the FRQ that you should have done last class. And you're getting 15 minutes for that, because that's how long you'll get on the test for one FRQ. Please do your homework.